This is the presentation for our WACB 2021 accepted paper, our two-level adversarial visual semantic coupling for generalized zero-shot learning. This work has been done in collaboration with Professor Vineet and Balasubramanian at IIT Hyderabad, India. We define the zero-shot learning problem here, in which we are given a training dataset of seen classes, and at test time, our model is supposed to generalize and recognize images from unseen classes that it has not seen during the training phase. We propose to address the zero-shot learning problem by learning to augment, where we generate unseen class features using a generative model and then train a classifier on the seen class features already provided in the training set and the generated unseen class features. Our proposed unified framework provides tight coupling between semantic and visual spaces and trains a model that is expressive enough to capture the data distribution of the underlying data well. We propose to augment the generative network with an inference network and then train them jointly to maximize the joint likelihood of visual semantic features. Learning the inference network helps us our model to capture the underlying modes of the data distribution well. We also use a two-level adversarial training strategy in which we use a joint maximization loss as an additional supervisory signal to facilitate better cross-domain knowledge transfer. We also train our model using a Wazistian center semantic alignment loss that helps us to model the joint distribution better. In addition to this, we use the representations which are adversarially learned by inference network to provide discriminative features for the final zero-shot recognition task. The generalized zero-shot learning problem can be thought as a problem of modeling joint probability Px given H given Y, where XHY denote the image features, semantic attributes, and class labels. These are the two factorizations of the joint probability, F1 and F2, and in our proposed approach, we use both these factorizations and use separate modules to model them. Here we show the model architecture. As you can see on the left hand side, we have our inference module, and on the right hand side, we have a generative module, and both of them communicate using a joint discriminator D3. The generative module learns a mapping from semantic space to image feature space, and the loss of the generative module is given by equation 3. The inference module does the opposite and learns a mapping from the image feature space to the attribute space as shown. Augmenting the generative model with the inference network and training them jointly helps our model to capture the modes of data distribution better. The loss for the inference module is shown by equation 4. The inference module and the generative module are jointly trained using an additional adversarial joint maximization loss. This is implemented using a joint discriminator D3, which is different from discriminators D1 and D2, and it discriminates between generated and real image and semantic features as shown, and tries to match the joint likelihood of visual and semantic features. Here we show the results on 4 benchmark datasets, CUB, FLO, AWA1 and AWA2. As we can see, our model gives state-of-the-art performance on all 4 of them for generalized zero-shot learning. We also visualize some generated features and plot them using TSNE. We see that the centers of the generated features and the unseen class features provided match for most of the classes, showing that our model is actually able to capture the modes of the data distribution well. We also show the GZSL error trajectory, and we can see the trajectory is pretty smooth, and our model converges very early in the trajectory. Here we also show the model performance with varying the number of synthesized unseen class features. As you can see, the green bars show the harmonic mean, which is the GZSL performance. As we can see, the performance is very stable with varying number of synthesized features. So this was the presentation of our proposed approach. Thank you.